All right, today we're going to be looking at chapter 2. It is atoms, molecules, and ions. First of all, we have Dalton's atomic theory. It's early 1800s. John Dalton started experimenting and came up with our current, our beginning theory of of atoms. First of all, he said elements are composed of extremely small particles, and he called those atoms. And that word comes from the Greek word atomos, which means not to cut or uncuttable. And so he just imagined like a billiard ball, a solid ball of extremely small particles. All atoms of a given element are identical, which have the same size, mass, and chemical properties. The atoms of one element are different from the atoms of all other elements. In other words, he thought that oxygen had its own little small atom, and nitrogen had its own little small atom, and they were different from each other because one was oxygen and one was nitrogen. But then all of the oxygen atoms would be identical, exactly the same, same mass, everything, and then all of the nitrogens would be exactly the same as each other. We now know that that's a little bit different. Number three, compounds are composed of atoms of more than one element. In any compound, the ratio of the numbers of the atoms of any two of the elements present is either an integer or a simple fraction. So this is basically, he determined that when atoms combine together, they come together in whole number ratios. So like 1 to 2 or 3 to 5 or 1 to 1. They don't come together in halves. So everything is a whole number ratio. Finally, a chemical reaction involves only the separation, combination, or rearrangement of atoms. It does not result in their creation or destruction. This is the law of conservation of mass. Basically, chemical reaction elements are rearranged, never created nor destroyed. Mass can't be created or destroyed. It just changes forms. And so that's where that last one comes from. We know that this is now in ordinary chemical reactions. We can create a new atom by slamming two together in a particle collider. And we also know that mass can be converted to energy. So this was the original first theory that was developed with experimentation. This is showing you just the whole number ratio law, where the law of multiple proportions, where we have carbon monoxide, which comes together in a 1 to 1 ratio, versus carbon dioxide, which comes together in a 2 to 1. Again, the law of multiple proportions. In this, we're showing that we have 16 atoms of element X. We have 8 atoms of element Y. They're going to combine together, and mass is going to be conserved. Okay, so this is the conservation of mass. You can't lose mass from start to finish. And this is why we balance equations. So both of these laws were developed out of Dalton's experiments, his theories on the atomic model. Then we jump forward just a little bit in experimentation. So we knew that atoms were small particles, but we didn't really know much about the makeup of an atom. And so we have J.J. Thomson, who came along with the cathode ray tube experiments. And he had these tubes full of inert gases and hooked up electricity to them, because we had electricity in at this time period, late 1800s. And he was able to determine that inside of these inert gases, there was both a positive and a negative charge. He put a charged plate above the ray it was basically a beam of light shining through, and it deflected the beam of light, the charged plates did. So the negatives caused it to deflect away, and the positives caused it to bend towards it. And so by this experiment, they were able to determine that there was not only a negative charge, but also a positive charge within these atoms. So this is basically the experiment. You have a cathode ray tube. You hook up electricity to it. You can see the light that is shining through. That these used to be in old TVs, really large set TVs. And then you put a bar magnet against it. Depending on which end you put up to it, it either bends away as it does here, or it bends towards it, and this would be an opposite charge. So here you would have a negative charge of the magnet, and it's pushing away the light, and this one is pulling it towards it. Millikan's experiment, this was just simply to measure the mass of an electron. We knew that it has a charge, a negative charge, as opposed to what we now know with protons with positive charges. But this is one where they wanted to measure the actual mass of it, and determined basically that the mass of electrons is very, very small. Electron's charge is negative 1.6 times 10 to the negative 19th coulombs. We're not going to use that to calculate or anything, just a fun fact. And then Thomson discovered or calculated the charge to mass ratio for the electron. The important thing you need to know about the Millikan experiment is just that we were able to determine the mass of electrons as opposed to what we would later determine the mass of protons and determine the ratio of how much larger protons were than electrons. Okay, so electron's mass is approximately 9.1 times 10 to the negative 28th grams, which is teeny, teeny, teeny. And then we have the other particles of the nucleus, which we would later determine was the nucleus. So they used radioactivity in the early 1900s. We were experimenting with uranium and different compounds, and determined that they gave off rays, which we were able to determine were alpha, gamma, and beta particles. And alpha particles were determined to be positive. You notice that they veer towards the negative plate. So that means that they're positive. Beta particles are negative, so they veer towards the positive plate. And gamma particles have no charge, so they just went straight through. Okay, you can't see them, but they have like a photographic plate here, so you can see where they end up. So J.J. Thomson, he was able to determine his model was positives and negatives. He imagined that we had positives scattered throughout and that the rest of it was all positive because they were able to determine the mass of electrons. They knew that in ratio to the positives, it was very tiny compared to the ratio of the positives. So imagine a total positive matrix here with negative electrons sprinkled throughout, and this was called the plum pudding model. The plum pudding model, and it was called that because he's from England, and plum pudding is similar to like a bread pudding or where you have raisins sprinkled throughout a matrix. And so this was his model, plum pudding model. Rutherford, he took that radioactivity, and he was using alpha particles. He was shooting them at gold foil. Again, alpha particles are invisible, so he's shooting it through, and he has like a detecting screen that's kind of like a photography paper that would pick up the rays. And what he determined was that most of the alpha particles went straight through it. Now, if Thomson's model was correct and it was a positive matrix, then they should have bounced back because there shouldn't have been any room for them to go through. But they didn't. They went straight through, and then some of them were deflected, like they got close to something that was positive because two positives would deflect from each other. So some of them were deflected, but every so often one would bounce back here, like it hit something solid. Okay, like it hit another positive charge. And so this is basically over here showing you what happened. Most of the positives were able to just go straight through because there's so much space between atoms. You have some that they got close to the nucleus, they deflected off. And then you have when they hit it head on, they flew backwards, okay? So he was able to determine that atoms' positive charges are concentrated in what he called the nucleus, very much like a cell's nucleus, and that the proton does have an opposite charge of the electron, whereas one is negative, the other is positive. So coming up with the proton, and that it is concentrated in the center of the atom, and that the rest of the atom is mostly empty space. Okay, so you can see here that the mass of a proton is 1,840 times greater than the mass of an electron, so tremendously larger. Rutherford's model then became the protons and neutrons. Well, they didn't know about neutrons yet, but protons and neutrons are in the middle, and that most of the atomic radius is based off of the electrons. Okay, so it's saying if the atom is the Houston Astrodome, then the nucleus is just a marble on the 50-yard line. So in terms of the size of an entire atom, the nucleus is tiny. Most of the volume is taken up by electrons. Chadwick came along and he discovered the neutrons. And so basically, whenever they were looking at Rutherford's model, they're saying, okay, well, if we have all positives in the middle, we have all negatives on the outside, then the negatives should go into the positive because their opposites attract. Or why are the positives that are centered in the middle not pushing away from each other? Because positives should push away from each other. And so we knew there's something else, some other particle that was holding it together. And Chadwick came up with, or determined that it was the neutron. And the neutrons basically um, were the buffer zone between the protons, and they were also part of the um, fundamental force of the nuclear force. Okay, the neutron is neutral; it doesn't have any charge, so we just have protons, which have positives, and electrons have negatives. The neutron is neutral, hence the name neutron. Okay, its mass is approximately it's close to the proton's mass. They're both approximately the same. So we give them an arbitrary value of 1 in terms of relative mass, and then we give the electron a relative mass of 0. Okay, so you can see here the masses in the grand scheme of things that neutrons are just a teeny bit more than protons. There's a reason for that, but we'll talk about that later. Electrons are very insignificant compared to all that. The charges, -1 for electrons, +1 for protons, and 0 for neutrons. Okay. The atomic number, which it has the symbol Z, it's the number of protons in the nucleus. So if you're looking at your periodic table and you look at lithium, lithium has an atomic number of 3, so it has 3 protons in the nucleus. If you look at calcium, calcium has an atomic number of 20, therefore it has 20 protons in the nucleus. The mass number, symbol A, is going to be the number of protons plus the number of neutrons in a single atom. Not the average of all of them, but just a single atom would be your mass number. And the mass number also equals the atomic number plus the number of neutrons. So if you know the atomic number and you know the mass number, you could subtract them and you could find the number of neutrons in an atom. Isotopes would be atoms of the same element, so they'd have the same Z, but they have different numbers of neutrons, so their overall mass number would be different. Okay, this is the symbol, the generic symbol. X would be where your symbol goes. So if it's calcium, it'd say Ca, and then Z would be 20, and then A would be whatever the mass tends to be, which most commonly for calcium would be 40. This is showing you the different isotopes of hydrogen. Hydrogen does have a atomic number of 1, and then it can have a mass of 1, 2, or 3. And this is just showing you the different ways that it's written. The D means deuterium, and this means tritium. It's just the different names that we give the different isotopes of hydrogen. This is showing you 2 different isotopes of uranium. You'll notice they have the same symbol, they have the same atomic number, but they do have different mass numbers because they have different numbers of neutrons, and makes one of them more stable. Sorry, you're looking at the 3 isotopes of hydrogen here. The only difference is that the number of neutrons. So when you have isotopes, the only difference in them is the number of neutrons. Therefore, the masses would be different. Giving the number of protons, neutrons, and electrons in each of the following species, you're going to look at your periodic table. In most atoms, if it's not in all atoms, if it's not a charged atom, then the number of protons and the number of electrons will be equal to each other. So in this atom of sodium, we have 11 protons, which means we also have 11 electrons. And then to find the number of neutrons, you would simply subtract 20 minus 11, and you would get 9 neutrons. On the second example, you would again still have 11 protons, 11 electrons, and then when you subtract, you get 11. So you would have 11 neutrons when you subtract those two numbers. This next one says 17 oxygen. It doesn't give you a bottom number, so you'd have to look at the periodic table to determine that. If you look on the periodic table, the atomic number for oxygen is 8. So we would have 8 protons, 8 electrons, and then when you subtract those two, you would get 9 neutrons. Carbon 14 is written a little bit differently, but it's the same as if we were to write it in this other format. We would just have C instead of Na here, and then you would have the 14 at the top. This is the mass number. This little number after is telling you the mass number. You can determine the bottom number by looking at the periodic table, and for carbon, it is 6. Okay, so you would have carbon 14 would have 6 protons, 6 electrons, and then 8 protons. On the modern periodic table, you can see here that we have metals, nonmetals, and metalloids. Oh, I don't do recycling. Mm-mm. Okay, so we have the modern periodic table. You have excuse me, metals, nonmetals, and metalloids. I apologize for that disruption there. Going across the periodic table, we have periods, which is why it's called the periodic table. It periodically repeats. Going down, we have groups or columns, which are also called families. Okay, and group one is called the alkali metals. Group 2 is the alkaline earth metals. Group 17 or 7A, depending on what you're looking at with your periodic table, are the halogens, and group 18 or 8A are the noble gases. Across the center of the periodic table, we have what are called the family of transition metals. At the bottom, we have the lanthanides and the actinides. So a molecule is just going to be 2 or more atoms held together by chemical forces. A diatomic element will only have 2 atoms, and so there are specific ones that are considered diatomic. You'll need to know these. Okay. When we talk about diatomic, typically we were talking about ones that have the same 2 atoms in them. Okay. And so typically we don't use diatomic to talk about like HCl or CO, even though they do have 2 atoms. We typically talk about for diatomic molecules ones that have the same ones. So on your periodic table, you can see we have H, N, O, F, Cl, Br, and I. These are called diatomic elements, and that means that they always come in twos. So you have H2, N2, O2, Br2, F2, Cl2. All of those are going to be in twos whenever they're alone. When they're bonded to something like here where H and Cl are bonded, you can have them individually. But when it's just Cl by itself, it'll be Cl2. Notice that it makes a 7 on your periodic table. And then if you count them, there's 1, 2, 3, 4, 5, 6. So we have to pick up hydrogen. It's your additional 7th one. Okay. These, when you write them, will always have a 2 subscript. Polyatomic molecules have more than 2 atoms. We'll specifically talk about polyatomic ions, but these are giving you some ideas of polyatomic molecules that have more than 2 atoms. An ion is just a group that does not have the same number of protons as it has, same number of electrons as it has protons. So you end up with a net charge, either positive or negative. So a cation will be one that has a positive charge. If something loses electrons, it loses negativity, therefore it becomes more positive. So if I have sodium, which has an atomic number of 11, and then it has 11 electrons, if it loses an electron and now has 10 electrons, and it has 11 protons, it now has a net positive 1 charge. Okay. If you have an anion will be one where it is actually gaining more electrons. So if you gain electrons, you become more negative because it is negative charge. And so if we have chlorine, which has 17 protons and 17 electrons, if we gain another electron so that we can fill our energy levels, we end up with a -1 charge because we have one more negative than we do positive. Monatomic ion only has 1 atom. And these are going to be important when we start naming, which we'll be doing in this chapter. Okay, so it only has one atom, and these would just be an element off the periodic table and then have a corresponding charge. Polyatomic ions, it's probably very important. Some of these you may want to write on the back of your periodic table. We use them a lot. So things like ammonium, this is ammonium, this is nitrate. And I think there's a list of polyatomic ions in this PowerPoint. Ones like sulfate, phosphate, acetate. There are certain ones that you may want to write down on the back of your periodic table so you do not forget them. Okay, this is just showing you common ions. What you need to get from this is that if your element is in group 1, it's going to end up with a +1 charge when it is an ion. If it's in group 2, it's going to get a +2 charge when it's an ion. Group 3A, 3 plus charge. Okay. If you're in group 7A, you'll have a -1 charge. If you're in 6A, you'll have a -2 charge. If you're in 5A, you'll have a -3. So you can see a pattern. So +1, +2, +3, -3, -2, -1. Okay, and that's when we're writing formulas that will use those charges. In the middle of the periodic table, these are called the transition elements. So they do tend to have different charges. I would highly suggest writing a few of these on your periodic table. I would write in the box for iron Fe2 plus or Fe3 plus, depends on which one we're dealing with. Copper 1 plus or copper 2 plus. Tin, and lead as well. Okay, I would do those charges, write those down so you'll know them. If you look here, there's like a little box, zinc, cadmium, and silver. These are monatomic ions. They only have one possible charge. So I need you to write those down on your periodic table. Zinc is always 2 plus, cadmium is 2 plus, and silver is always going to be a 1 plus. Formulas and models. So we have hydrogen, water, ammonia, methane. These are common names, water, ammonia, methane, as opposed to IUPAC names, which we'll learn how to do. We can look at the structural formula. These would be how they're done in space without the Lewis structure. And then this would be your typical ball and stick model. So there's different ways that we can model these things depending on what we're trying to see. This would be a space filling model where it actually shows you how much space the atom takes up. The molecular formula is going to show you the exact number of elements, whereas an empirical formula will show you the simplest ratio. So let's see if they give us an example. So if I have a molecular formula of H2O, I cannot reduce that. It's just 2 to 1. And so the empirical would be exactly the same thing, H2O. If I have glucose, which is C6H12O6, I could reduce that. Everything is divisible by 6. And so my empirical would be CH2O. So the empirical is just basically the reduced formula if you could reduce it. O3, molecular, there's only one atom. We can't divide that by anything. So the empirical, well, I guess they're going to show it as 0. That makes sense. When you're doing an experiment, if you get an empirical formula of just 1, it could be by any factor. That was my mistake there. N2H4, if we were to reduce that, we could divide everything by 2, and then that would be NH2. This is saying write the molecular formula of methylamine, which is colorless gas. You would count the number of atoms. You have 2 of the reds. Reds typically are oxygens, and then you have on here gray, which is typically not a color. So I'm assuming they're trying to use N. Okay. So it says there are 5 H atoms, 1 carbon atom, 1 nitrogen atom. Therefore, it is CH5N. I don't think that matches that particular thing. Mm, I don't think that matches that particular thing. I think this is a bad example, guys. That's 2 oxygens shown. And then either the outside ones are supposed to be hydrogen or nitrogen, and I don't see that being any of this formula. So that's going to be an error, I think, right there. Okay, write the empirical formulas for the following. You're just going to reduce those. You can go through and do those. Ionic compounds are going to consist of a combination of a positive and a negative, always positive and a negative because those are what attract to each other. So you have a cation and an anion, and the formula will be the same as the empirical. So you're always going to have the lowest ratio when you are putting those together. The sum of the charges on the cations will equal 0 unless for some reason you have what's called a polyatomic ion, which you will have a natural charge. The most reactive metals are going to be in groups 1 and 2 because they're only giving up 1 or 2 electrons, and the most reactive nonmetals will be group 7A, which is the halogens, because they need 1 electron to fill their outer energy levels. So formulas of ionic compounds. We have here aluminum 3 plus, oxygen 2 negative. And so what is going to happen is if I said I want you to write aluminum oxide, you would look on the periodic table, find aluminum. I told you it was going to be a 3 plus. You should have wrote that on your periodic table. You would find oxygen. You can see that it was going to be a 2 negative. And then all you're going to simply do is take the charges without the pluses and minuses, and you're going to take that number and crisscross it down to the other atom. So in what's happening is basically you're saying I'm going to need 3 oxygens, because that would be -6, and I'm going to need 2 aluminums, that would be +6, and they'll cancel out the charges with each other. Okay, so you're crisscrossing the numbers. So here we have Ca2 plus and Br -1. We're going to crisscross the numbers. The 2 is going to come over to the Br and come down. The 1 from the bromine is going to come down. The charges go away. They'll cancel each other out. We'll end up with 2 negatives because we have 2 bromines. We'll end up with 2 positives because we have 1 calcium, and then those 2 charges will equal 0. So what you're basically doing is just crisscrossing the charges so that you can end up with a charge of 0. Here we have sodium, which is a +1 ion, and we have carbonate, which is a polyatomic ion that has a charge of 2 negative. And so whenever we crisscross, we do end up with Na2CO3 because when you have one of these, that's -2, and you have 2 of these, that's +2, so we end up with it balancing out. The easiest way to do formulas of ionic compounds, you just crisscross the numbers and let the charges go away. So if we're writing a formula for magnesium nitride, we have Mg2 plus and we have N3 negative. We'll crisscross these numbers. That 3 will come down to the magnesium. That 2 will come down to the nitrogen. You'll end up with Mg3N2. Okay, Mg3N2. So you can see here, they showed you the crisscross. The 2 comes down over here. The 3 comes down over here. Crisscross the numbers. Writing names. So ionic compounds, it's going to typically be a metal and a non-metal. That's how you'll know it's ionic. And you're going to just change the ending of the non-metal to IDE. So instead of being chlorine, it would be chloride. Instead of being fluorine, it would be fluoride. So we have BaCl2. You'll name the first element first, so barium. And then you have chlorine. And we're going to change the ending to ide, so it'd be chloride. So we have barium chloride. The next one we have K, which is potassium, and we have oxygen. We're going to change the ending of oxygen to ide, so it'll be oxide, and so we'll end up with potassium oxide. We have magnesium, Mg. OH is a polyatomic ion, which if, like I said, you go farther along in the PowerPoint, you'll find the list of polyatomic ions. OH is called hydroxide, and so here we have magnesium hydroxide. Doesn't matter how many we have because those numbers are simply there because we crisscrossed. KNO3. K is going to be potassium. NO3, I happen to know, is a polyatomic ion, which is called nitrate. So it is important that you know the polyatomic ions. And so here we have potassium nitrate. Transition metals. If you have a metal that is in the middle, or if you have lead or tin, you're going to have a Roman numeral when you write the names. So we have FeCl2. Okay, so FeCl2, we know it's going to be iron. I already told you to write +2 or +3 with your iron, so it can only be one or the other. If we look at it, we see that we have a 2 here with Cl, so that means that we have to have basically a 2 over here because we know Cl has a charge of -1. If Cl has a charge of -1, this side will be -2, so this side needs to be +2. So we have iron 2, and then we're going to change the ending again to IDE, so we'll have iron 2 chloride. Okay, Roman numerals 1 through 7 is what you'll need. This next one, you can see the difference that we have a 3 at the bottom, which means that we have 3 chlorines, so that's going to be -3 charge there. Iron would have to be a +3, and so we'll end up with iron 3 chloride. So that's the difference in how those two look. And so when you have a transition metal in the middle, or if you have one that has more than one charge, so um, zinc, silver, cadmium will not have Roman numerals because they only have one charge. I told you to write those on the periodic table. So +2, plus 2 for cadmium, and then +1 for silver. Cr2s3, Cr is chromium. It is located in the middle, and then sulfur is sulfur. So we'll change the ending to sulfur to sulfide. But if we uncrisscross, basically, sulfur is a 2 negative, and I have 3 of them. So that's -6. And so I need a +6 off chromium, and I have 2 of them. So that would have to be +3. Okay. So chromium 3 sulfide. This is just showing you how most of the nonmetals, the endings would be like oxide, sulfide, chloride. This is your got a mixture of your polyatomic ions within it. It's kind of, they're kind of all mixed in, but the majority of your polyatomic ions will be negative. Some very common ones: carbonate, chlorate, um, cyanide, nitrate, phosphates, sulfates. So kind of go through those and become familiar with them. So you're naming the following compounds. You're going to look, and iron is in the middle of the periodic table, so we will need a Roman numeral. And then if you go back to the previous slide, you'll see that nitrate is a -1. Nitrate is a -1, and I have 2 of them. That means that's -2, which means that iron would have to be +2. So we'd have iron 2 nitrate. The next one, we have sodium. Sodium is a +1. It is not in the center, so we do not need a Roman numeral. And then we have HPO4, which if you look on the polyatomic ions is hydrogen phosphate. So we would have sodium hydrogen phosphate. And then we have NH4, which is a polyatomic ion called ammonium. And we have SO3, which is a polyatomic ion called sulfite. And when you have 2 polyatomic ions together, you just name them both. So this would be ammonium sulfite. All right, write chemical formulas for the following compounds. So when you're doing this, you're going to want to write the formula with the charge, and then you're going to crisscross them. So mercury would be Hg. It tells you it's mercury 1. So mercury Hg +1. Nitrite is going to be NO2 -1. That's from the list of polyatomic ions. They're both -1s, so you'd end up with HgNO2. Okay, cesium, same thing. So you do CS. CS is in the first group, so it would be +1. Sulfide is S2 negative, and then you would crisscross, you would get CS2S. And then do the same for calcium phosphate. Calcium phosphate, you have calcium, which is in the second column, so it's Ca2 plus. You have phosphate, which is polyatomic ion, which is PO4, 3 negative. Then you would crisscross them, and you would get Ca3, PO4 parentheses 2. So when you have a polyatomic ion and you need a number on the outside, you will put parentheses around it. Okay, this is just showing you the formulas. And I do see here on the mercury 1, it's giving you Hg2 2 plus. And so that they're using that as polyatomic ion, which is why it's showing you the formula it is. Molecular compounds, nonmetals, or a nonmetal and a metalloid. Okay, so these would be how you would know they'd be molecular. And they have some very common names, so like water, ammonia, methane, but we also have the IUPAC names. Okay, so the element that is the furthest to the left, or as we'll later learn, the one with the lowest electronegativity is typically the first one. So we're going to go with the one that is farthest to the left in a period and closest to the bottom will be put first in the formula. Okay, if more than one compound can be formed from the same elements, use prefixes. So these are the prefixes. You'll need to write these probably on the back of your periodic table if you do not know them. We have mono, di, tri, tetra, penta, hexahepta, we won't go above 10, but these prefixes will be added to tell you how many of atoms we have, as opposed to in the ionic ones, we did not put prefixes. So do not mix these two naming conventions. One is for molecular and one is for ionic. We're still going to change the last part of the second one to IDE. That has not changed from with the ionic. So I have HI. So H, hydrogen, I is iodine, which we would change to iodide. And so we have hydrogen iodide. All hydrogen compounds, you won't put a prefix on the second one. However, if you don't have a hydrogen compound, you will put a prefix. Like this would be hydrogen monoiodide, which would not be incorrect. Okay. In F3, we have nitrogen, and then we have fluorine, which would be fluoride. And so you'll tell me I have nitrogen, and then I have 3 fluorines, so I have trifluoride. Okay, so the numbers in these matter. They didn't matter in ionic because that was from us crisscrossing. We don't crisscross in molecular, so we need to know the numbers. SO2, you have sulfur, and then you have oxygen, which would be oxide. So we have sulfur dioxide. Into Cl4, we need to put a prefix on the nitrogen, so this would be dinitrogen, and then 4 would be tetra, and we have chlorine, which would be chloride. So dinitrogen tetrachloride. NO2, again, nitrogen, and then 2 oxygens would be dioxide. N2O, in this particular case, we have 2 nitrogens, which would be di, and we have 1 oxygen, which is going to be mono. So we end up with dinitrogen monoxide. Notice the difference between here where we have 1 and we've used a mono, and then in the hydrogen compounds, we don't use the mono. It's just the convention. Okay, you can go through and name these so that you know what you're doing with those. And then write the formulas from here. When you're writing the formulas, it's just a backwards version. So carbon disulfide, you would put C and then S and then a 2 after it so that you know how many you had. Or disilicon, that would be Si2. Hexabromide would be Br hexa 6. So this is just a flow chart that you can copy down, just kind of showing you, is it ionic or molecular? That's the first thing you have to figure out. If it's ionic, then use the conventions for naming for that. And then if it is molecular, use the conventions for naming with that. An acid is something that when you dissolve it in water, it gives us hydrogen protons or hydrogen ions, which is just a proton. So we have HCl gas and we have HCl in water, and we put it in water, it becomes hydrochloric acid. Okay, so when it's pure substance, it's hydrogen chloride. When you put it in water, it's called hydrochloric acid. So that's the difference between that. And when it dissolves in water, you get a H plus, which connects to water, which makes it H3O, which is called hydronium. And then you have chlorine, just chlorine ions just floating around. These are your common acids. So when you have hydrogen attached to just a nonmetal, you'll say hydro, and then whatever. So we have hydrofluoric, hydrochloric, and you can see the rest of those. Oops, sorry. And then hydrosulfuric. CN is cyanide. That's going to be one of your polyatomic ions. So that's where hydrocyanic acid comes from. An oxyacid or oxoacid is one that has oxygen in it as well, and so they're named differently than the ones that do not have oxygen in them. So HNO3, which is just nitrate ion with a hydrogen, and nitrate, we'll change the ending from 8 and change it to ic, and it will become nitric acid. Okay. CO3 is carbonate. We'll change the ending of carbonate to ic, and it'll become carbonic acid. Notice we don't name the hydrogen part. So we're not saying hydronitric acid. We don't do that. We just name the polyatomic ion. And if the ending is 8, we change it to ic. If the ending of the polyatomic ion is ITE or ite, we're going to change it to us. Okay. I don't know if they have an example of that in here, but we would change it to OUS. Okay, so this is the endings of these. This is nitrate, carbonate, and phosphate, and we're going to change the endings of all of those to ic. This is, here it is right here. So oxyacids, if you have your reference whatever your reference was, like carbonate, then you would change it to ic acid. And if you have another oxygen, so let me use chlorate as an example. Chlorate has ClO3 in it. And so if we made an acid out of that, we would have chloric acid, like we would here. And if we add another oxygen, so we have ClO4, then we have perchloric acid. If we have um, uh, ClO2, so one less oxygen, you can see here is one less oxygen, we have chlorous acid. And if we have yet another one, so we just have ClO, then we have hypochlorous acid. Okay. And so these are the ions it's telling you. So you have chlorate, chlorite, hypochlorite, and perchlorate, or perchlorate, sorry. When all of the hydrogens are removed from the ic acid, the anion's name will be 8. So that's what I just told you. All the 8s are getting changed to ic. All the ites are being changed to us when you're going to acids, and then vice versa the other way. Okay. Um, so this is showing you if we are removing hydrogens, the difference between phosphate, hydrogen phosphate, and dihydrogen phosphate. Um, so you can see phosphate has a -3 charge, hydrogen phosphate has a -2 charge, and dihydrogen phosphate has a -1 charge. And that is because as you add hydrogen, it's H pluses, and so the charge goes down by 1. I'll let you go through those. Okay, a base. A base is something that typically increases the OH or the hydroxide concentration. OH negative is hydroxide. Okay, so we have sodium hydroxide, and when we put it into water, it does dissociate into the sodium ion and the hydroxide ion. Same with potassium hydroxide and barium hydroxide. So when barium hydroxide dissociates, it actually adds 2 hydroxides to the water as opposed to the other ones. Hydrates are going to be things that have a specific number of water molecules attached to them, so it's part of their chemical formula. So this is barium chloride, and then it would be dihydrate. Okay, you have 2 waters. Okay, so you'll name the number of waters with the prefix, and then you rename the ionic part like you normally would. So here we have LiCl, which is lithium chloride, and we only have 1 water, so we end up with monohydrate. MgSO4, which happens to be Epsom salt. So we have magnesium sulfate, and then 7, which is hepta. So we have magnesium sulfate heptahydrate. And this is just how you name hydrates. Next one, we have SR. SR is going to be strontium. We have strontium nitrate. And then 4 is tetra, so tetrahydrate. Okay, this is showing you the difference between a hydrated copper sulfate, which has a really pretty blue color, and then when you dehydrate it, basically you heat it up and you drive off all that water, it turns into just a white powder. Organic chemistry, we'll just talk briefly about organic chemistry. The functional groups, we have different groups that you can add to the end of compounds. You can add OHs, which is an alcohol group. This main group is going to be that's a methyl group. Um, and so this is methanol because we have methane, CH4 is methane. Instead of having another hydrogen, we added in an OH, was an alcohol group, and we're going to change the ending to OL. Okay, in this particular one, we're adding an amine group on this one. This is still methane, CH4. The original one was methane, and we're adding an amine group to it. So we end up with methyl, and then we have the amine group, and so we end up with methylamine, or methylamine is how it's pronounced. And then we have this one, which is added a C double bond OOH to it, which is an acid group. And so we end up with our methyl group, and then we have that, and so we end up with acetic acid. This is an acetate group added onto this. So this is the common name. Acetic acid is the common name for this. And so we'll talk more about, I think, later how to name organic molecules. So on this, the first 10 straight ones, when they talk about alkanes, alkanes means everything has single bonds. We don't have double or triples. And so the endings will all be anes. And you can see the beginning ones, it goes meth, eth, prop, bute. And so you have methane, ethane, propane, butane. You've probably heard of these because these are typical things that we burn for fossil fuels. And then you have pentane, hexane, heptane, octane, which is in your gasoline, right? Nonane and decane. So these are prefixes that can be added to different endings for us to do organic chemistry.